On mixed forced and self-oscillations with delays in elasticity and friction. Alishir Alifov, Mechanical Engineering Research Institute of Russian Academy of Sciences, Moscow, Russia. Model and equations of motion. Frictional self-oscillations are described very well by the model shown in Figure 1. Body 1 with mass m lies on the belt, which is driven by engine having a torque characteristic, where is the speed of rotation of the main rate. The friction force Tu varying between the body 1 and the tape depends on the relative speed u. Under certain conditions, it can cause self-oscillations of body 1. The body is affected by an external force. The elastic and friction forces depends on the delay, i.e. they occur respectively C1, x tau and Tu delta. Here, x tau is equal x t minus tau. Time derivative x delta is time derivative t minus delta, where tau and delta are constant time delay factors. On the figure 1, we can see system model. The equations of motion of the system have the form 1. U delta is equal v minus time derivative x delta, v is equal r0 time derivative phi. Let's represent the characteristics of the force as a function in form 2. Here, T0 is the normal reaction force. Delta 1 and delta 3 are positive constants. Sin U delta is equal 1 at U delta greater 0, and sin U delta is equal minus 1 at U delta less 0. Form 2 is widely used in practice. It was also observed when considering the problem of measuring friction forces in space conditions. Solving equations by direct linearization. Using the direct linearization method, we replace the part in function 2 with the function 3, where b, f, and kf are given by indicated ratios. Here v and 2 and 3 are equal by the equations. They symbolize the linearization accuracy parameter, and the choice of the interval of its value is not limited. It can be selected in the interval from 0 to 2. Equations once based on 3 take the next form by 4. B and K are given by indicated relations. The desired solutions, taking into account the next relations, have the next form, where V is equal AP comes from. The solutions for determining the amplitude A, the phase zeta of the oscillations, and the velocity of energy source omega at u greater than or equal to V are as follows. 5. Where A, E, and U are given by the indicated relations. From 5 for time derivative A is equal to 0 and time derivative zeta is equal to 0, follow the equations for determining the characteristics of stationary self-oscillations. Their amplitude is determined by the next ratio, 6. The load S on the energy source is determined by the third equation, 5, for time derivative u is equal to 0. In the case of u greater than or equal AV, the expression for calculating it looks like the next ratio. Using the equation m minus s is equal to 0, stationary values of the velocity u are calculated, which can also be determined by the intersection point of the curves m and s. Stability of stationary movements. Stationary movements must be investigated for stability. For this purpose, we create equations in variations 4, 5, and use Hurwitz criteria. Stability criteria are as follows. 7. Stationary movements are stable if condition 7 are met. For u greater than or equal AV, speeds we have the next relations. In the case of u less than or equal AP, the first criterion 7 is almost always satisfied due to the dependence of AP is approximately equal to u. The determining factor is the second criterion that can be represented in the next form, where S is approximately equal to this relation, taking into account AP is approximately given to U. After calculation, in figure 2, we can see amplitude frequency curves for delta is equal P divided by 2. On figure 3, we can see amplitude frequency curves for delta is equal P. And finally, on figure 4, we can see amplitude frequency curves for delta is equal 3 P divided by 2. Thank you for attention.